So the last thing that we did, in our last consult, oh, let me also say something because I can't just plug. So we have a first year graduate student named Maurice, and I'm not gonna try his last name right at the moment because it would be just embarrassing. But he sent me an abstract for the math club talk last night. It sounded totally interesting. He's actually going to tackle some category theory. He's got an interesting background in physics as well as math, so this should be a fun one. So I encourage you all to show up for that if you got the time. So pick up where we left off here. So we have an integral domain. All the conditions are equivalent. One, R is the Dedekind domain. Two, R is enclosed. Period. And dimension of R is no more than one. And remember, in the case that the dimension is equal to zero, that's kind of the silly Dedekind domain in the sense that it's field. And three, R is Euclidean. And R localized M is a Euclidean valuation domain. For all n in max spec R. I put the Noetherian and evaluation domain kind of for emphasis because once R is Noetherian, then localization has to be Noetherian. But I did point out last time that just this is not enough. You need Noetherian plus this assumption as well. Okay. So the last time we did one implies two last time. And so we'll pick up two plus three. So we have that R is integrally closed in period and dimension is less than or equal to 1. So we want to show that R is Noetherian and our localized M is Noetherian valuation domain. R is Noetherian, is immediate, because after all, it is an assumption in number 2. So really what we need to do is show that R localized M is a valuation domain for every maximum ideal. So let's go for a contradiction here. Let us suppose that for some M, R localized M is not a Noetherian valuation. Of course, since we already know that R is Noetherian, R localized M must be Noetherian. So really what we're assuming is that R localized M is not a valuation domain. And in fact, here's what we do know. by the assumption of two, we know that R is in the period, so R localized in is the period. We know that R is intervally closed, and so R localized in is intervally closed. So those two are okay, but what we don't know is that R is PID. Because if our localized domain were a PID, then it would be in the theory evaluation domain because it's a local PID. So we were going to abuse the notation a little bit. So let's suppose that R is local with maximal ideal M. So let's suppose so what I want to do is I'm going to show that if I've got a situation here, so let's take them aside here. Suppose R is local with maximal ideal M, and the theory. So of course that's in my assumption local. So suppose that R, what we have is a local domain, maximal ideal M generated by n elements, and let X be a non-zero non-unit of M. So this is kind of key. Then, yes.
Are we making a distinction between what everybody usually calls quasi-local and local?
Well, we don't have to here because everything's in the theory. Right, so usually what local means is quasi-local plus it's Noetherian. But in my situation here, everything's Noetherian. Here's the interesting thing about this. So we have, and this is local and one-dimensional. Suppose you have X and M. Now take the ideal generated by the principal ideal X and look at the radical of X. What is that?
The intersection of all prime ideals continue.
Okay, that's the important observation right there. It's the intersection of all prime ideals that contain it. What are all the prime ideals that contain it? Well, this ring only has two primes, doesn't it? It's got 0, which X is not in, and then it's got the maximal ideal, because we know that this is one-dimensional and it's local, so there's only one maximal ideal. So, and since it's one-dimensional, that's it. So the radical of this is all of M. Right. So in particular, any one of these generators, if you take a big enough power of it, is going to be divisible by X. Right. And in fact, if you take a high enough power of the maximal ideal itself, it'll be inside there. So in particular, we can find some fixed natural number M such that that's some natural number M such that M is big enough to flash all these generators down here, such that A I to the M is in the ideal generated by X for all I between 1 and N. Now, what I want to do now is let Y equal A1 to the M minus 1. Now, what happens? What can you say about m times y? That's right, because anything in M is a linear combination of these. And when a linear combination of this hits this thing, it knocks this into X. So with this observation, we can point out so y over X is an element of M inverse. That is, when you hit anything in M by y over X, you end up back in the ring. Right, so it's in the inverse of that. Now, let me also make the other observation. Note. If my equals X, well, let me ask you, what conclusion can we come to then if my equals X?
So it's invertible.
Right, right. In fact, principle done, right? We'll have our contradiction, right? So we can assume that M inverse, right. Strictly contains R. And so if you look at M inverse, this must contain M. Right? This has to contain M. And so so let's focus on this. We know that M times M inverse is actually contained in R, right? And it must contain M. If M inverse equals R, then what can we conclude? Well, we can conclude that M is invertible. And hence, well, if M times M inverse is invertible, then it must be principal in this case. Why? What do we know about R? It's local, right? And hence, principal as R local. And once again, right? So, we must conclude then that M times M inverse M inverse must equal M. And so, what's the significance of this? What happens if M inverse? M times its inverse is equal to maximal ideal. Well, this means for all x in M inverse, that has to hold, right? If M inverse is equal to M, but if you take anything in M inverse and multiply by M, it has to be contained in M, right? And M is finitely generated. And what does this mean? Well, this means, so each such X is integral over R. Because the image is finitely generated module that you need. Therefore, M inverse is contained in R as R is integrally closed. And there we cut off the final path. Contradiction. And so this includes the 2 implies 3. Finally, I think that's kind of a sweet proof. Finally, for 3 implies 1, so yes.
Why should we assume that R was local?
This is really my R localized at M. I started over again, so I didn't have to use the R localized at M every time. So in the first step of our proof, we noticed that R localized at M was a Noetherian value, was interval closed. And I changed the notation from R localized at M to just R. And I said, okay, now it's local with this maximal ideal M. So that's why I said
this M is different than the M than the previous M.
So yeah, this is the same situation we have because R localized at M was local, it was integrally closed, and it was Noetherian. But instead of writing R localized at M every time and doing that, I just shortened the notation. So this is the same R as R localized at M. I just took this to just looked at this in the local case. Okay, 3 implies 1, I think is not too bad. Because what we have to do is, we have to show, recall, since I've erased it, R is Noetherian, and R localized at M is Noetherian diagonalization. In my spec. And I want to show that this implies that R is Dedekind. And in fact, it suffices to show for ordinary ideals. Let I and R be an ideal, non-zero. Notice that as R is Noetherian, this is actually important here. I is finitely generated. So in other words, it's got a chance of being invertible, right? We need to go the full 9 here and show that in fact it is invertible. And how do we do this? Well. So. I M is, let's see, what do we got here? I M is principal. Well, let me add this parenthesis. In my spec. Because after all, our localized it in, it's in the theory evaluation domain, so it's PID. Right, and that's really all we need to know here. So I M is principal. Since I is locally principal. And finitely generated. Then I is invertible. If you look back to that theorem that we had earlier, you need actually the ideal to be both locally principal and finitely generated to be invertible. You might ask yourself, what happens if you jerk out the Noetherian here? What happens if you just worry about ideals that are, locally principal? They don't have to be invertible. We gave an example of that, but you get a class of rings called almost Dedekind domains. Almost Dedekind domains are, so that is just for culture's sake, so to speak. Definition. A domain R is almost Dedekind. If R localized M is a Noetherian vibration. All M and max spec. Of course, any Dedekind domain is almost Dedekind, as whenever you start putting other modifiers in there, it better make sense. Notice that every PID is a Dedekind domain. Every Dedekind domain is almost Dedekind. And every almost Dedekind domain. Well, right. There are PIDs. All PIDs are Dedekind, but there are Dedekind domains that are not PIDs. Take any ring of algebraic integers, it's not PID. Z adjoined with the square root -5 would be nicely. There are proofer domains that are not almost Dedekind. Let me rip off a quick example because I'm a lazy man. Any valuation domain of dimension more than one is proofer, but it's not almost Dedekind. There are almost Dedekind domains that aren't Dedekind, otherwise I've wasted the last 5 minutes of your life. We've seen an example of this, the one where I had the prime splitting off. That's an example of something that's almost Dedekind. Not Dedekind. Oops, almost Dedekind. Anything proof for enjoys. So all the nice properties, proof domains, and very long Dedekind domains, but almost Dedekind domains are, have dimension less than or equal to 1. So they share that with Dedekind domains. Their dimension is always less than or equal to 1. You can't stack the primes higher than 0 plus a non-trivial maximum. And of course, all fields are almost Dedekind. And one of the things about Dedekind domains that are cool is if you take any non-zero ideal, you can factor it uniquely into a product of prime ideals, right? You cannot do this in almost Dedekind domains in general, because otherwise it would be a Dedekind domain. But almost Dedekind domains are precisely the domains that have ideal cancellation. Sounds like a good homework problem. Let me go see if I can do it first. This is the way I like to think about it. So you don't get unique factorization necessarily to prime ideals, but what we do get is you get something like, you get cancellation in the monoid of the ideals. That is, if you have I times A equals I times B, then it's the case that A is. Okay, any questions on that? Oh, and I guess this is kind of a plug for on Friday. On Friday, I am going to skip out on my office hours for a while because we've got my former student Richard coming in, who is going to give a talk. And
Friday?
yeah, Friday. Is today a weekday, man? Yes.
Okay.
It will be Friday in 8 AM. Richard's going to give a talk, and Richard is something of an expert on almost Dedekind things actually. So I think it's going to be at 11. So you might mark your calendar for that. Okay, so let me give you a theorem that I say in my notes that I'm going to prove. We will prove this later. That's a lie. It is proved later in the notes, but I'm going to skip over this. But this is an important. The proof is more than I want to get into. I want to get into some other stuff that I think is fun, but this is a big, huge, whopping theorem. And I'm going to give you a couple of examples to go with this and show you why. Are a one-dimensional theorem domain with quotient field. Okay, so you've got it's got two things that I want. It's one-dimensional. And I really do mean one-dimensional because the case where it's, well, you'll see, let's state this here. But it'll be one-dimensional and it's the theorem if T is an overring. That is to say, some ring between R and its quotient field, then T is one-dimensional. And this is a crazy cool result. And it's the failure of this. Yes, as the Emperor and Star Wars said, failure of this out of any of these parameters is complete. It's very bad. It feels very bad if you remove either one of these hypotheses. Let me point out why I do say R is one dimensional. If R is zero dimensional, Noetherian domain, then it's a field, and the theorem is stupid because quotient field is K itself, right? R and K are the same thing, right? So, for example, if you have these are really, really nice, tame examples, I think, of two-dimensional Noetherian domains, right? It turns out, just for giggles, it turns out if you have a Noetherian domain, Noetherian ring, and you join a polynomial variable to it, the dimension increases by one. You don't have to worry about either that 2n plus 1, but it just increases by one. And of course, it's still Noetherian. So if you have a Noetherian ring and you join n polynomial variables to it, so if you start with n dimensional, if you have a Noetherian ring and you join n polynomial variables to it, it increases the dimension by n, right? So these are both two-dimensional. In fact, they're UFDs. Very nice. Does anybody see a non-Noetherian overring of this?
Y divided by X, Y divided by X.
Yes.
Yeah.
Right, you can do this sort of business. You can get a lot of mileage out of this kind of construction, and you can do the same thing here. All you get overring Z. X over 2, X over 4, X over 8. You can pull this kind of business right. But this theorem will actually be quite useful to us in just a moment. Let me give you a quick corollary to this. First, use the corollary. If R is Noetherian and dimension of R equals 1, then the integral closure of R is Dedekind. So Dedekind domains always have to be one-dimensional Noetherian and integral closed, but this theorem actually tells you something. If I walk up to you on the street and I give you a one-dimensional Noetherian domain, you can build a Dedekind domain just by taking its integral closure. Always works, right? And let me just sketch out why this corollary is true. Proof. In R1 and R Noetherian.
Use the fact that the integral closures are overing.
Right. Okay. Right. By definition, the integral closure is everything in the quotient field that's the root of some monic polynomial with coefficients in R. So the integral closure of R is an overring. By theorem 823, R bar is one-dimensional and Noetherian. Right. So since R bar is also integral closed, R bar is Dedekind. By the way, to capture the one-dimensional part, we really don't need theory 2, 3. Because if you start with any if you start with a domain of any dimension and you look at its integral closure, it has to have the same dimension, because that's one of the theorems we had earlier, that inequality preserves Kroll dimension. Now here's a big number theory theorem. And this is, one might say that this is kind of a big piece of the machinery that makes number theory, algebraic number theory, interesting. There are 825. Let R be a domain with quotient field. And F a finite extension then when the integral closure of R and F that so here's kind of the diagram. So if you start with R and it's got a quotient field K, and you take a finite extension if you take the integral closure of R, oh, of course I didn't. There's a very important there we go. Works for any domain, you know, with math, right? All we have to do is take the integral closure and stick. So if you take a finite extension of K and you take the integral closure of R in F, then this thing is also big. And so this is kind of a big thing that you do in algebraic number theory. You start with everybody's favorite Dedekind domain C, take Q, take finite extension of Q, stay at 3n, it's a 3n extension, and you let this ring of algebraic integers. And this theorem is what allows you to do this. Z is in fact is better than Dedekind, it's PID, but any such ring of algebraic integers by this theorem is Dedekind. And so even though it may not be a PID anymore, at least it's got the property that all its non-zero proper ideals factor into prime ideals, and it's got all the other nice properties of Dedekind. Notice, let me make another observation. We had the same theorem for proof of domains with the word here finite replaced by algebraic, right? What do we need finite here for? Well, actually, we don't really need it, because in some cases, it's possible for this extension to be infinite and this still be Dedekind, but it's delicate. If you do it at random, then it's probably not going to be Dedekind anymore. It's going to lose the theoreminess. The finiteness here, this all works for proof, no problemo. The finite here is basically to keep this thing Noetherian, because proof of domains, Dedekind domains are Noetherian proof of domains. And this finiteness, it kind of ropes in, it keeps things from getting out of hand. It is possible to be infinite and still be Noetherian in some special cases, but you can't count on it in general. So let me make this a little bit more concrete here. So the first thing to notice is earlier stuff, we know R F is true. Because finite extensions are algebra. Because what we had in the proof domain case was this was an algebraic extension, and the integral, and we actually went through the proof of that this thing is proof from. So the only thing that you really have to notice here is that any finite extension fields here is automatically algebraic, right? And so we get this proof from. So it remains to show that this integral closure in F is Noetherian. Okay. Any idea on how we might do that?
Prove it's finitely generated molecule.
Okay. So let's let so the fact that this is finite means this is a finite extension, so I can write this as a U1, U2 up to UN as vector space of F. We can also assume UI is in RF. I mean, all these UIs actually come out of F, which is the quotient field of this. And so we can certainly multiply by an appropriate denominator, put this back down here. Right. So we can make the additional assumption, and this will make our life a little bit easier, that each of these are in F. So let P naught equal R joined with U1, U2, UN. Look at this ring right here. What do we know about this? Well, yeah, that's integral, and so let me go through kind of a list of things I need. First of all, one, T naught is nothing. Why? Right, so let me point out first that R adjoined with X1, X2, Xn is Noetherian. By the Hilbert basis there, right? And this surjects onto by the map that takes each xi to ui. And so T naught is a homomorphic image of an Noetherian ring. Okay, so we've got that. So T naught is Noetherian. What else do I want? I know that T naught is one dimensional. And how do I know that?
It's integral and integral serves.
That's right. As it is integral over R. And the dimension of R is this. Right. But that was important that I scribbled that Dedekind in there at the last minute because that wouldn't work anymore. So what have I done? I've taken R and I've joined in integral elements, and step by step, this is an integral extension. All right. Okay. So what do we have? We have that it is Noetherian. Its dimension is 1. Now, it's not necessarily integer closed. And in fact, you might see an example of that from that one homework where we looked at rings of algebraic integers in the quadratic case. I might have actually joined some stuff that doesn't get full closure, but notice that the integral closure of T naught is this. So RF is integral closure of one-dimensional Noetherian ring. Domain. So RF is and that does it. Okay. Any questions on this? So I think this is probably a good place to break for the day, because next time I'm gonna start talking a little bit more about Dedekind domains now that we've got this kind of sort of the basic big picture stuff. And I am going to get more specific with class groups, especially in rings of integers and certain domains, Dedekind domains where you can play some games. I'm going to prove the correlates theorem, and we're going to talk about elasticity and all kinds of good stuff like that. Okay, any questions? All right, well, think about the math club for this Friday, also Richard's talk. Other than that, I will see you on Friday.